Hello, this chat is part of the World Leaders series, and I have a true world leader with me. Leslie Lamport is known to many as the father of principal distributed computing. He gained a degree in mathematics at MIT in 1960, and he's worked with a range of companies including SRI International and DEC. And since 2001, he has been a principal computer scientist at Microsoft Research. Leslie has won so many awards for his work, including being a three-time winner of the prestigious Dijkstra Prize in Distributed Computing and in winning the IEEE John von Neumann Medal. In 2014, he won the ACM Turing Prize, which many see as the Nobel Prize of Computer Science. His work has included groundbreaking work on distributed systems, and he was the initial creator of LaTeX. Leslie's work has been cited over 87,000 times, and his work on time clocks and the ordering of events in a distributed system is one of the most cited works in computer science ever. Okay, hi, Leslie.
Hello.
And so you built LaTeX. What were the magic elements that have made it so successful, and where does it go in the future?
Well, first of all, I have nothing to do with where it's going in the future. One of the best decisions I've ever made was to, 1995, to give it over to what is now the LaTeX 3 group. And so I'm just a user like everybody else. The timing was right. Don Knuth had just released, or was in the process of finalizing the final version of tech. And I was aware that people would need a macro package on top of that for using it. And I was planning to write a book at the time, and I would need a macro package for that. So I figured it wouldn't be too much extra work to just make it something that would be useful for everyone. And it wasn't too much work. And why it's been successful, I guess why many people like it and some people hate it. But there's one of the things, or perhaps the thing that's made me most successful is it was Edgar Dijkstra who actually told it to somebody else. And he said that I have a remarkable ability at abstraction. And, I think that was a perceptive observation. And in some sense, what I did was abstract away, try to abstract away the typesetting from document production and try, in principle, to get people to be thinking about, writing, not typesetting. And also, I was inspired by Brian Reed's scribe system. And I suspect that one of the reasons LaTeX was successful was that Brian decided to sell scribe to some company that was then selling it. And it's hard to compete with something that's free.
So in 1978, you created or you wrote one of the most cited papers of all time in computer science on clocks. What was the concept that you outlined, and how has it changed the modern world?
Well, what happened is that Bob Thomas, and I'm now blocking on the name of this co-author, anyway, sent me a preprint of a paper for implementing a distributed database. And I realized that there was a problem with their algorithm. And the problem was that it could order operations to the database in a way that violated causality, in the sense that one command that logically preceded another could wind up being ordered, in the wrong direction. And it was not too hard to fix their algorithm for doing to do that. And but to do that, needed to explain the concept of causality. And the reason it was the correct definition was obvious to me, because it's very similar to the notion of causality in special relativity. The idea is that one event can causally can affect another event if a beam of light, basically, from generated by the first event to the place where the second event happens, arrives before that second event. And basically just change the idea of a beam of light to a message in the network. And you have the definition of causality. And that seemed to blow people away. It was something that, was being perfectly obvious to me. And the other thing that was, again, this ability of abstraction is their algorithm was for implementing a distributed database. But I realized that their algorithm could more generally implement what I call, or what people call, a state machine. A state machine is something that, think of it as a Turing machine, perhaps. No, not a Turing machine. A bad analogy. Something that receives inputs. As a result of an input, it will change its state. As a result of the input and its current state, it will change its state and produce an output. And what I realized is that, well, first, any system that one wants to build can be thought of as a state machine. And that the problem that needed to be solved to build a distributed system is to get all of the computers in the system to collaborate to implement a single state machine. And the key to doing that was for them to agree on the order of the commands. And I don't know if that generalization was obvious to Thomas and his co-author, but it was obvious to me. And the amusing thing is that people read the paper and remembered this causality concept, but forgot completely about the state machine, the idea of the algorithm being used to implement a state machine. And on 2 occasions, some people have told me that there was nothing about state machines in that paper, and I had to go back and look at the paper to make sure that I wasn't going crazy. But some people, and I think Butler Lamson was probably the the primary person to recognize that was the significance of thinking about a distributed system in terms of implementing a state machine. And also Fred Schneider popularized that idea by basically writing a paper about thinking of distributed systems and as implementing a state machine.
So in 1979, you created a foundation block for hash-based signatures, which are obviously now used in post-quantum signatures. I think they're now known as the Lamport signature. Do you know how these signatures are being used at the current time in creating quantum robust signatures?
Okay, there are two algorithms I've created that are both called Lamport signatures, and I think the one you're talking about is one in which you can basically sign a single bit using a one-way function by publishing two say 64-bit or something values, and one of them is the result of how does it work? Okay, you sign the bit by saying which of those two values is represents the correct bit, and you can prove that that's correct because you've generated those two bits by a one-way function, so nobody else can do that. At any rate, I haven't been thinking about this recently, so I can't describe it very coherently. And basically, nobody used it because it required a lot of bits just to sign a single bit of a message. Now, of course, that's not quite so bad because you can use a one-way hash function to create a hash of the message and just sign the hash. But actually, you've got the date wrong, and that one was not published in 79. That one was, in fact, published in the Diffie-Hellman famous paper that started public key cryptography, which I believe was 75. And it's become apparently it's become, I mean, that was totally made obsolete or uninteresting by RSA, which is more powerful. But RSA, if quantum computing can really be developed into its potential, then RSA becomes insecure. But my method doesn't. So that's why it might be interesting. And the story of that algorithm came about because Whit Diffie was a friend of mine, and we were sitting together in a coffee house in Berkeley, and he posed the problem of digital signatures, and I said, "Gee, that doesn't sound very hard." And I thought about it a minute, and I just wrote down my algorithm on a paper napkin, and Whit and Marty put it in their paper.
That's amazing. We have spoken to Marty Hellman and Whitfield Diffie, and we even saw the desk that Marty Hellman wrote, the basic discrete log problem that became the Diffie-Hellman method. So your Lamport signature was actually before the Diffie-Hellman paper. That's interesting.
Yeah. In fact,
And
before
then,
anybody else had heard of the problem of digital signatures.
yeah, that's excellent. And you've generally not patented your work. Obviously, the RSA paper was patented, and the authors of that did very well. Why have you generally avoided patents and published your work?
Well, in those days, patenting algorithms was very rare, and as a matter of fact, it wasn't even clear that one could do it. And it never occurred to me that anyone could make money doing that. And at any rate, even if it did, it would be the company I was working for that would presumably own the patent. And I didn't start making patent. I guess I started when I was working at the DEC Systems Research Center. They liked it if you had patents, and so I started patenting, and basically patents evolved into being a purely defensive measure. People wanted to, companies wanted to have a set of patents that if somebody threatened them with a lawsuit about a patent, they could counter and say, well, you're violating this patent of ours, so let's just forget about it.
In 1981, I think you wrote a paper on the Byzantine generals problem. Can you outline how the method works and why it's so important in modern system?
Well, actually, the date was 77. And
I need to check all my dates.
It's easy to remember because there was a general belief that you could get fault tolerance to protect against a single failure by basically using three computers, and so and making your decision by majority voting, so that if one computer was bad and it came out with the wrong result, well, the other two would outvote it. But I realized that it was not quite so simple, and that if one of the computers failed in such a way that it gave different information to the two different computers, then a simple solution of majority voting doesn't work, because you wind up with basically each computer can't tell whether which of the other two computers is the bad one. And so what this could do is the two good computers have no way of knowing that they should be cooperating with one another. And I recognized that problem, but I also knew that there was a solution to it. And that solution came by using digital signatures. Because if the bad guy had to sign the messages that he sent to the two others, then if he sends different messages to the two others, then the two others can compare notes and realize that he's the bad guy because he was the only one who could have signed those messages. So that if, for instance, you would know that it wasn't me who was the bad one, because I could show you that because I couldn't have signed this message of the bad guy, and so I couldn't have produced the messages that he sent. Anyway, and of course, having learned about digital signatures, I knew that with that, and could come up with an algorithm for solving the problem. At the time, I didn't think of signatures, of digital signatures, as really being necessary. That is, that you really had to protect against a malicious guy. I figured that there would probably be some way that you could implement them that was cheaper than, say, my method for doing it, that would work with high probability against random failures. But, I left that as a problem for somebody else, and nobody ever did. And people believe that that you need these digital signature algorithms that work against malicious agents to implement these algorithms. And I still have a belief that they could be implemented more cheaply, but nowadays computers are much faster, and there's no need to, that. And there are, RSA digital signature algorithms that are fast enough that you don't need anything faster. At any rate, and I came to I joined SRI in '77 after inventing that algorithm with digital signature, and discovered that they had been working on that same problem. But the solutions they found without digital signatures required 4 processors, 4 computers, to protect against a single failure rather than 3. And they had proved that that was necessary. They hadn't thought about using digital signatures. So under the assumptions that, which basically ruled out digital signatures, it was impossible to do it with fewer than 4 computers. And so, I joined with them. There's Marshall Pease and Rob Shostak, who were the other 2. Rob found the first algorithm which for handling a single failure with 4 processors, and Marshall generalized that to handling n failures with 3n plus 1 computers. And so the 3 of us published a paper and called it, interactive consistency, the problem of interactive consistency. Well, I realized that this was an important problem that people needed to pay attention to. And I learned one thing from Dijkstra, which was the importance of having a story. Because Dijkstra invented this problem that he called the dining philosopher's problem. And it never seemed to me to be a terribly important problem. I mean, Dijkstra is brilliant and he did some marvelous things. And I thought that the dining philosophers was just, a very minor thing compared to other things he did. But it received a lot of attention because it had a cute story. And the cute story was a bunch of philosophers that, it's amusing that he was Dutch. The way you would do it today is that, each person shared a chopstick with his 2 neighbors. And so in order to eat, someone had to get both chopsticks, but there needed to be an algorithm that you didn't wind up in a situation where everybody, grabbed one chopstick and nobody could eat. It became the dining philosopher's problem. The amusing thing is that being Dutch in those days, Chinese food was very esoteric. He described it as needing, some kind of funny spaghetti that needed 2 forks to eat it. Anyway, so I realized that I needed a story to popularize this result of ours, which is very important because the reason the people at SRI were doing it was that NASA, and which actually at that time was actually NACA, some other acronym. But at any rate, they would want to realize that the future of avionics was that computers would be flying the airplanes. and people, there will be computers between what the person wants to do and how the commands go out to the different parts of the airplane. And they needed to build very reliable computers, computer system, which required multiple computers to protect against failure. And so this problem arose from them, and making airplanes fly safely is an important thing, and I thought people should be aware of it. So I invented the Byzantine generals problem, which consisted of a bunch of generals which needed to decide, whether to attack or to retreat, and that, if some of them attacked, but some of them retreated, they would lose. So they had to agree that, all agree, but that some of the generals could be traitors. And that became the Byzantine generals problem. And it was very successful because of, at gaining attention because of that huge story behind it.
And you also worked on temporal logic of action. How do you think this could be used in real life systems?
Shall I go into the story of the history of my? This all started, back when I got interested in concurrency, and I read a paper that described a solution to the mutual exclusion problem, the problem had been invented by Dijkstra. And it's a multi-process problem. And I thought, that was so complicated, I thought I could do something better. And I whipped something off, and it was for 2 processors, sent it to the CACM journal. And a couple of weeks later, I received a reply from the editor saying, here's the bug in your algorithm. And that had 2 effects. The first was that I realized that concurrent algorithms were really tricky, and you needed to have good proof of correctness of your algorithm. And the second was that I was going to solve that damn problem, and that led to the bakery algorithm, but that's a different story, which we'll probably get to later, I imagine. But at any rate, this led me to the interest of how to write rigorous correctness proofs of algorithms. And that evolved over the years. In 77, that was in 1972, developed 72 or 73, I'm not sure, the bakery algorithm. In 77, Amir Pnueli introduced temporal logic to computer science as a way of reasoning about programs. And I recognize that as a very good way of reasoning about doing part of the job of reasoning. There are sort of 2 different kinds of properties that you want to prove about a program, which I've called safety and liveness. Safety basically means that it doesn't do the wrong thing. And liveness means it eventually does something. So in our program, you need both: a program that just stops and does nothing, never does anything wrong. But doing something isn't of much use if you do the wrong thing. So that's why, and it turns out that I realized those are 2 very different classes of problems that you reason about in different ways. And temporal logic seemed, I discovered, worked great for reasoning about aliveness, but not for safety. And at any rate, over the years, I developed, somewhere along the line, I realized that, reasoning means mathematics. And the way to reason about an algorithm is to describe mathematically what the algorithm does. And I could describe the liveness properties of the algorithm with temporal logic, but basically I described the safety part by describing the algorithm as a state machine. And over the years, I sort of refined this method and got it to be sort of cleaner and more mathematical, but it was still, these two different parts, the safety part and the liveness part. And then what I realized is that by basically lots of people had the idea of trying to describe completely both safety and liveness programs with temporal logic. And it obviously couldn't be done with the original very simple logic that Pinelli introduced. So people introduced more and more complicated kinds of temporal operators of temporality. Basically, Pinelli's logic was just based on a single temporal notion of something being true always for all times. But then they added that, one thing is true and until another thing is true, and this thing is true on every other Tuesday. And it just became a mess. And I tried, that approach, and I realized it just didn't work. So I, had this two-part approach with state machines, and for safety and temporal logic for liveness. And then I realized that there was a very simple way of extending Pinelli's original logic that didn't add new temporal operators, but basically instead of, what the basic formulas were about states, saying property of the state. But I added the notion of an action, which is a property of pairs of states. And in particular, it's described a state machine by the property of a property on a pair of states, which says whether it's, the first state, the second state is a possible next state of the first state. And by that changed the temporal logic, which is produced this temporal logic TLA. I could describe a program with a single formula in a very natural way. And the mathematics just completely fell into place. So TLA is important for that respect, but its practical significance is, well, how shall I put that? Okay, it has a practical significant application with TLA plus, because TLA is the basic logic. But then I had to build a complete language around it called TLA plus, and I realized that when trying to describe, the problem that I discovered was important, in those intervening years, was that people were building complicated systems, and they couldn't describe precisely what those systems did, and so what they didn't have is some good way to write a high-level description of what this system was doing, or at least critical parts of it, because the critical aspects of it involved concurrency, and that was very hard to get right. So I was working on how to get engineers who were building these systems to write these high-level abstract descriptions of what the system was doing, and use them as the building block for, as the starting point for, writing that design before you start building the system. And particularly to discover errors at that level. And those kinds of errors, especially concurrency errors, are very hard to discover by debugging. And even if you're lucky enough to find them by debugging, it's very hard to fix them at that level because you have a whole bunch of code. So you want to catch those errors in the design stage. So I was, proselytizing that. And TLA gave me now a language to use that. And what I realized was that the important part of the thing that makes TLA nice is that most of the reasoning and most of the actual part of the formula that you're writing is ordinary math. And just a few temporal logic operators just needed where you're talking about. So if you weren't talking about liveness at all, the formula would have, just, Penueli's box operator, which says always. And you might have, a couple of thousand lines of mathematics if it were a complicated system. And then there would just be one box. For adding the liveness, you need, a few more operators, but literally, if, once you did, you might have a couple of thousand of lines describing the safety part, and then using the things you divide into those couple of thousand lines, you just have maybe, a half dozen or a dozen lines that involve temporal operators that describe the safety, the liveness rather. So most of the action going on was in this mathematics. And I realized that the important thing in designing the systems, is not the TLA, not the temporal logic, but basically describing the state machine mathematically. And so I designed this very mathematical language. And, it's very different when people were working in temporal logic. Temporal logic, you have some, you add some temporal operators like box on top of what are basically ordinary vanilla mathematical formulas. And they were always interested in, the temporal part, the box part, all of that stuff. And if they wrote a language, they would just put something like a programming language that has integers and a couple of things, and then you can build everything like that from a Turing machine. You can build anything in a program, starting from just arithmetic and Boolean operators or something. And they didn't give very much thought to that part of the language. But I realized that it was that math part was the real important thing about TLA plus, that it was ordinary math. And so what I did is spend, all of my effort on getting a very powerful and expressive language of mathematics embedded in and it's mostly that math that's the design that you write. And what I also believe, and I've seen it happen, is that the real benefit of using it is learning to think mathematically about what you're doing, because it forces you to think mathematically, because you have to describe your system mathematically. And getting to learn to think mathematically improves your thinking and improves your designs. So what's magical about TLA plus is not TLA plus, it's math. And, it's based on, very classical, math, but it forces you to learn to describe your system in terms of ordinary mathematics. And that really improves your thinking and improves your designs.
So you outlined that you worked on the problem of mutual exclusion with the bakery algorithm. Thank you for setting that up there. So what's the bakery algorithm?
Well, it's a beautiful algorithm. I mean, I really have the feeling that I didn't invent it; I discovered it. The mutual exclusion problem arises when you have multiple processes accessing some resource. So, for instance, here you have, back in the time sharing days, lots of people were sharing the same computer, running their own programs, and all these people might want to use the printer, but you can only have one program at a time using the printer. So the different processes had to synchronize each other. So that only one process at a time was using the printer. And using the printer is just might be, doing any particular thing, so that you have some specific piece of code that only one process at a time can be executed, and that's solving the mutual exclusion problem. And Dijkstra proposed it and proposed solutions. And the thing about all the other solutions was that underneath them, they were based on some mutual exclusion. For example, if they're usually were made shared memory, well, that meant that, processes had to read and write the same memory location. Well, they can't read and write at the same time, so they had to have lower level mutual exclusion, provided by the hardware that allowed them to have mutually exclusive access to that memory register in order to solve the higher level mutual exclusion problem. And the beautiful thing about the bakery algorithm, and in fact, people, somebody wrote a book saying that that was necessary. The only way you can solve mutual exclusion was to do that. And even in the 1990s, the ACM produced some. They had some self-teaching courses of computer thing, and they had questions, or they provided exams, and the quote correct answer to one of the exams basically said that in order to implement mutual exclusion, you had to use lower level mutual exclusion. Well, the beautiful thing about the bakery algorithm, which was invented 20 years or so before that CACM test, was that it solved mutual exclusion without using any lower level mutual exclusion. And it used shared memory, but it had the property that that the shared memory could actually be used concurrently without mutual exclusion. The algorithm required used memory registers which were only written by a single process, but read by other processes. And these had the amazing property that if a read occurred while the write was going on, the read could return any value, and the algorithm still worked. And so, for instance, if one process, the process that sort of was the writer of that memory register, we're changing it, from 27 to 49, a process reading it wouldn't necessarily get 27 or 49. While that read was happening, might get 796, and the algorithm still worked. And I didn't even, set out to write an algorithm that did it. It was when I wrote a correctness proof of that algorithm, I realized that it didn't depend on the value. Correctness didn't depend on what value was read while it was being written. So, I not only stumbled on the algorithm, I stumbled on its, marvelous property. It's of, no practical value. In fact, mutual, exclusion algorithms had no practical value after maybe the 1970s or something, because people started building hardware to that with instructions that made it very easy to implement mutual exclusion. It would pop up occasionally, though, when you had new designs. For example, sometimes you might need mutual exclusion in a network. And so you had to have a mutual exclusion algorithm that worked by message passing. So, that would, you need an algorithm for that. But by and large, those algorithms have been designed, and mutual exclusion is not an interesting problem anymore. But it is, a very fundamental concept. So, if anybody ever comes up with a real, well, lots of people, especially in the days when I started, were looking for the Turing machine of concurrency. That is, the Turing machine turned out to be this model of sequential computation that is, just incredibly important, that encapsulated in a simple way the very concept of computational complexity and stuff. And people were looking for, the Turing machine of concurrent algorithms, the ones that, all you need to do is, describe, solving the problem for this Turing machine, tells you something. And that work never led anywhere. The closest has come is what's called, process algebra, that people use for something, but that was never interesting for me, because my interest was in what is called correctness, although it's a very technical, it's using a technical term. That is, correctness means that the program satisfies a property, that you can look at a single behavior of this program by itself and decide whether or not it satisfies that property. So, for example, average execution time is not a correctness property, because looking at any single behavior, you can't tell what the average of multiple behaviors are. So, but it's this concept of correctness, of concurrent algorithms, which interested me, and that's process algebra is not appropriate for that problem. It's good for other things.
Great. And you wanted to find the Paxos algorithm, I think, which was quite complex to understand. So you tried to simplify it. What was the simplification?
Well, I don't believe it's complex. I think it's very simple. But the Paxos algorithm, by the way, is, it basically solves the problem that Byzantine generals was trying to solve, but it wasn't solving it for malicious failure. It's solving it for the normal failure, where you can assume that, it's for multiple computers communicating, and you assume that when a computer fails, it just stops. It doesn't start, sending different things to different other processes. And, 99.9% of the time, that's the way, processes fail. So, so if you make this assumption, then you can come up with much more efficient algorithms. And so Paxos was an efficient, an algorithm for, again, implementing an arbitrary state machine by a collection of processes that would only have benign failures. By the way, also, Butler Lamson was really very crucial in, he's one of the few people, well, I made the mistake of writing, of trying to do the same thing I'd written with Byzantine generals and come up with a story behind Paxos. And that was a mistake. The story was too complicated. And people were not able to see the simple algorithm behind the the story. And Butler Lamson was one of the few people who did understand it, and he explained what was going on to engineers, and that's one reason why it became popular. By the way, the Paxos algorithm was discovered independently by two people at MIT, Brian Oakey, who was part of his thesis, and which was under the supervision of Barbara Liskov. And so it's sort of, and they called it time-stamped replication. And it's essentially the same algorithm, although they described it for a particular use in a particular system. And the original papers didn't describe its general use, in terms of implementing a state machine. And, I've always assumed that they understood the generality, but maybe they didn't understand it until they read my paper. I don't know. But at any rate, so the paper the algorithm, I think, is very simple. And at least but maybe it's simple to me because I think mathematically about these things. But I tried it at one conference, was it for PODC conference in distributed computing, and I just decided to explain it to somebody, and I was able to explain it to this person on a walk, in about 5 minutes, and they had no problem understanding it. Of course, they were perhaps smarter than most people. Being good computer science, it was a woman who was a good computer scientist. But so at any rate, so I just wrote a paper called Paxos Made Simple that tried to describe it in non-mathematical terms. And there's an interesting thing about that. An engineer at Amazon sent me emails saying that there was one sentence in that paper that could be misinterpreted. And if it were interpreted the wrong way, one would come up with an incorrect algorithm. And he said he'd looked through several open source implementations of Paxos, and a number of them had that error. They wrote it from that paper. And so I didn't correct the error in the paper. On my publication page, I have little blurbs about each of the papers, and in the publication page for that paper, it says this paper has this problem, and if you want to implement Paxos, you should read the original paper, which gives a mathematical description of the algorithm. And while the story is maybe a little baroque, the description of the algorithm is very quite mathematical and quite you can deal with mathematics. You have no trouble finding the correct the actual algorithm. So I'm just telling people, don't program in, don't design your programs in English. Do it in mathematics.
And you also defined the concept of the part-time parliament. Can you quickly give us an overview of what that involves?
Well, the part-time parliament is, the basic, in building a state machine, the basic problem is getting the different processes to decide on what each command is. Because once you know what the commands are and what the starting state of the state machine, you know what the state machine does. And so underneath an implementation of a state machine, is the Byzantine generalist algorithm, for example, is solving this problem of choosing a single command. Okay, I'm just wondering which. Okay, so in Paxos, it uses the story is based on a parliament, and the interesting part of Paxos is the algorithm that the parliament uses to choose the next law that they're passing. And so that's basically at the heart of the Paxos algorithm. Not worth trying to explain the algorithm now.
In 2013, you received the ACM Turing Award. I think Bill Gates said Leslie has done great things not just in the field of computer science, but also in making the world a safer place. Countless people around the world benefit from his work without ever hearing his name. Leslie is a fantastic example of what can be possible when the world's brightest minds are encouraged to push the boundaries of what's possible. So for all the work that you've done in your life, what do you think is your greatest achievement?
Well, I think Bill Gates or whoever wrote that to him got a little carried away. That really exaggerates the importance of what I've done. The internet would have been invented very well without me. It pretty much would look pretty much the same. I think if it helped, people say that Time Clocks paper has helped them think about distributed systems, and well, if it's helped them, I'm glad. I think Jim Gray said shortly after that paper was published that he had gotten people had two reactions to it. Some people thought it was brilliant, and some people thought it was trivial. And what I say is, I can't argue with the second opinion, and I'm not inclined to argue with the first opinion. But, I really, it's hard for me to understand how why it has had such a large effect on people, because to me it really did seem so trivial.
Yeah. And as you said, some people would say that you created theoretical infrastructure for the construction of the internet. How do you think your concepts that you created enabled the internet to happen?
Well, they never say exactly how it helped, and I don't know. I would like to think that people are started. That I've taught people to think mathematically at a higher level about what they're building before they actually start coding it. But I see very little of that actually going on, and certainly not at the time that the internet was being built. So, I would like to think that that's my, an influence that I've had on the world. But right now, I don't see it having that much influence. People, there's still this thought of, agile programming is the wonderful thing, which is, program first, think later. And which is exactly the wrong way of doing things. If you're really creating something, like a concurrent algorithm, that need to get right. I mean, I think there may be good reason for building a prototype and doing it very quickly and seeing what works and what doesn't. And little programming I do, sometimes I will code first, not to develop an idea, but because I want to figure out how I can get these silly programming languages to do what I want them to do. And I have to find out, what is feasible for me to do by myself. My programs are the ones I write for myself. What's feasible for me to do in a reasonable amount of time using these complicated and hard to understand languages. But even when I build a program, I will spend, usually a few weeks just thinking about what the program is going to do and how it does it. And, I found that saves me enormous amount of time. And what usually happens is that I start out having this thinking about what I was going to build, it's this fairly complicated thing. And what I discover, what I realize out of thinking, is how I can simplify what it does, that I didn't need to do all of those things and come down to just the essentials of what needs to be done and come up with a very simple, much simpler problem and a simpler design that's much easier to program. And that works in practice. Are you still there?
Yep.
I'm sorry, because something weird on my computer. There's a bunch of people used TLA Plus to design a system. Well, they built this system that was a real-time operating system that flew on an European Space Agency's space probe. So it's a real piece of real programming. And they decided for the next version they would just start from scratch. And they decided that they were going to use TLA Plus to actually write their high-level design in TLA Plus. And they wrote a book about it. I had no idea, I knew nothing about it. And what they report is that because they wrote it in TLA Plus first and did this design, this new version had 1/10 as much code as the previous version. And, you don't get, program something with 1/10 as much code, by better programming. You do it by mathematical thinking. Now, this is very rare, not because it couldn't happen again, but the way TLA Plus is used mostly is not designing a complete system. It's designing some algorithm that's being used inside the system, an algorithm that involves concurrency. And so they're just using it to implement a very small part of a large system. And so, they don't get that kind of, code reduction. They just get that part of the system, working correctly. Although what I am told is that, people think that there's this idea that, if you're going to write things formally, well, it means you have to simplify them in order to be able to do it. So things get simpler and, therefore, not as efficient. Well, what I've been told, by people at Amazon, was that by writing the design of this piece of the code in TLA Plus, and then using our tools to check it, they've been able to make optimizations that they wouldn't have dared to do before, because they had no way of being sure that confident that they would work.